Welcome to Unit 1, Lesson 2, which is a review of factoring techniques. Factoring is really just the opposite of multiplying different polynomials together. So instead of multiplying them together into one final product, we're taking an expression that's kind of like a final product and breaking it up into separate pieces that would then multiply back into that original polynomial that we're given. Now, factoring is something you would have learned last year in grade 10, and you would have learned a few different techniques for it, which we're all going to review in this lesson. But it's also really important to remember that when we're factoring, we always need to look for the greatest common factor first, which means common factoring itself is the type of factoring we need to make sure we review and understand before we go any further in this. So let's do that with this first one. So common factoring means we're going to find literally a common factor to each of our different terms that we have in our expression. And we'll write that common factor in front of the whole thing and then create a bracket beside it, which represents everything that's left over once we've divided by the common factor. Now, to find a common factor, what I need to do first is think about the coefficients. So here I have -9 and +6, and I try and find a number that divides evenly by both of those, or in other words, is a common factor of both of those numbers. So 3 is an example of those. But instead of just making 3 part of my common factor, another little convention that we use in math is that if that first term happens to be negative, like in this case we have -9, it's really useful if you also factor out the negative as well. So I'm actually going to factor out -3. But our common factor won't always just have a number part to it. We also want to look for any powers of our variable that happen to be common to both terms. Now, if you notice, the variable y only actually appears in the second term. So nothing to do with y can be part of our common factor at all. But both of those terms at least have an x to the power of 1 inside of them. So that means x to the power of 1 is quite literally common to both, and so that's part of our common factor. So our common factor now is out in front, and now, as I said, we're going to create a bracket beside it, and the bracket's going to have pieces that represent what's left over when our original polynomial gets divided by our common factor. So we take -9x and divide by -3x, and we just get the number +3. Take +6xy, divide it by -3x, and we get -2y. So that is our final common factored form. And what we've arrived at here, this factored version of our original expression, is actually the exact same expression that we started with, just written in a new form. And what we'll see is that often this factored form of a polynomial can be much more useful to us for lots of different calculations or for solving processes that we might do in the future. But you can prove to yourself that this really is the exact same thing we started with if you take the -3x and you expand it by multiplying it by each piece in that bracket. You'll end up with the exact same original polynomial that we started with. Let's try doing another one of these. So now in example B here, we've got 3 different pieces to it. So let's look for a common factor. Well, if we look at the coefficients, 8, -6, and 2, they all divide evenly by 2. And then if I look at the x's, well, they all not only have an x, the 2 of them actually have an x squared and 1 of them has an x cubed, which means the biggest power of x that they at least all have is they at least all have 2 powers of x, or in other words, they each have at least an x squared. Now, of course, that middle term actually has an x cubed, so it has like an extra power of x as well. We can say they all at least have x to the power of 2. So x squared becomes part of that common factor. We can also say in terms of the y's that they all have at least 1 power of y. But again, that last term only has y to the power of 1, so that's as much as we can include as our common factor. So now what's left over? Well, we divide that first term by our common factor, we would get 4, and using exponent laws with our y's, would leave us with y squared. We would have, well, -3, and then x to the power of 1, y to the power of 2. And then actually that last term is exactly the same as our common factor, so they would divide out perfectly and just leave +1. So that process is what we call common factoring. And it's something that no matter what other types of factoring we learn and attempt to do in the future, we're always going to take every expression we want to factor and try and do this common factoring step first. Let's look at some other ways we can factor though. So another really important way is called difference of squares. And it only pops up in certain special situations. The special situations that produce it look something like this. And it's where the name difference of squares come from. It's when we have two different things that are each squared, so that's what the A and the B are representing, and then there's a subtraction between them. So if we have two things that are both perfect squares, then we can easily square root them. So in other words, the square root of A squared is just A, and the square root of B squared is just B. Well, it turns out when we have something that is in this difference of squares form like this, it will always break down into factors that look like so, where one of the brackets will be the square root of the first thing minus the square root of the second, and the other bracket is the square root of the first thing added with the square root of the second. So in other words, we just need to focus on how to square root each of our pieces and then combine them together correctly in the bracket after. So let's review how to do that. So here, 4x squared can be easily square rooted, and so can the number 1. So here we have a difference of squares, two things being subtracted from each other, and they're both things that can be easily square rooted. Well, the square root of the square root of 4x squared is 2x. So that means 2x is going to be at the beginning of each of my two brackets. One of them is going to be added with my other piece, the other one's going to be subtracted with my other piece. Then to find the other piece, I just take the number 1 and I square root that as well. And I actually also get the number 1. So it's 2x plus 1 and 2x minus 1 is my final form of this result. Let's look at another one with a little bit more going on. So now, well, 36x squared, once again, that can be square rooted. And so can 25y to the power of 4. Well, 36x squared, when I square root it, I would get 6x. That's going to be added with something. And here 6x is going to need to be subtracted with something. To finish off those brackets, I take 25y to the power of 4 and square root it. Well, 25 square rooted is 5. And then y to the power of 4, when I square root that, it cuts its exponent in half. Remember we talked about that in a previous lesson, that when we are square rooting something that has an exponent on it, we just cut its exponent in half. And this would be minus 5y squared for the same reason. Let's try a couple more that are similar but have additional little tricks to watch out for. So here for this one, once again, tackle it in the same way. The square root of 81 is 9, and the square root of a to the power of 4 is a cubed. So I'm going to do 9 minus a cubed, or you could do the plus 1 first. It doesn't actually matter whether you do the minus or the plus, as long as we have both. But then we also have to be careful because we're not quite done. Turns out this, even further, would also be a difference of squares. Now notice that this one is not a difference of squares because it's not a difference. Those things are being added. But the first bracket actually is a difference of squares. So it's going to break up into 3 minus a and 3 plus a. Or again, I could have written those in the opposite order if I wanted to. It doesn't matter which order you write them in. But then the 9 plus a squared part is still hanging off the end, and there's nothing more that we can do with that. And let's do one more that's going to combine this idea of difference of squares, but also force us to remember that important rule that we talked about at the very beginning of this note, that we should always technically be looking for any common factors first. Now, For these last three examples we did before this one, there were no common factors. But in this case, both of these can be evenly divided by 3, and they both have at least one power of a. Not only that, but the first term is negative, so I'm going to make my common factor -3, and I also have a power of a. So -3a is going to be my common factor, which means left over I have a to the power of 6, b to the power of 4, and minus 16 now. When I take positive 48a divided by -3a, I get minus 16. Well, a to the power of 6 and b to the power of 4, that looks weird, but it's actually very easy to square root that, because we just take each of those exponents and cut them in half. And we know that 16 can be easily square rooted as well, so this truly is, the thing that we have in the bracket is a difference of squares that we can now break down further. So we have -3a still out in front. Remember, it's just coming along for the ride. But now we have a cubed b squared, that's the square root of the first piece. And we can do it subtracted with the square root of the second, and also show it being added with the square root of the second. And again, you could do those in the opposite order if you want. It doesn't matter which order the brackets are written in.